Okay, AP Physics 1. Today we are going to be starting a new unit, Unit 6, Work and Energy. And with the exception of probably forces and Newton's laws, this is arguably the most important unit we're going to be focusing on in this course. But before we jump into it and start really talking about the main lesson for today, let's talk about energy for a few minutes. Energy is a concept you're definitely familiar with. And unfortunately, it's a concept that also doesn't have a very obvious and clear definition. So let's talk about what we do know. Well, we know that we require energy to do stuff, whatever that stuff might be. If we want to move around or we want to exercise, well, we require food to do that, to keep our body operating. If we want to power a car so that it can drive, we need to provide it with gasoline to power the engine. And if we want to use our cell phone for whatever reason, we need to power it with electricity from the wall that's stored in its battery. And so we can kind of see that energy is really fuel. It allows us to do stuff. And we're pretty familiar with this because up to this point, you've talked about energy in your other science classes. It's come up in both biology and chemistry, and we've really talked about the idea, and I'm sure you're familiar with this, that energy is a conserved quantity. It does not just pop into existence or disappears. It just gets transferred or can change from one form to another. Now, one more important thing to mention is that energy, compared to many of the concepts we've been discussing in this class, is a somewhat new concept. And by that I mean that, when we talked about forces and momentum, Isaac Newton formalized a lot of that, and a lot of that went back to Galileo and previous thinkers. But this idea of energy was not discussed at that time, so that would have been really the 16 and 1700s. It really began to come to the fore in the 1800s, specifically with the Industrial Revolution. Engineers and physicists and chemists were trying to figure out a way to study how powering many of these machines and devices would allow them to do stuff as well as produce heat, and what exact quantities could we use to study these systems. And to do that, the concept of energy that we now know it was developed to help try to answer those questions. And now we have a framework for looking at physics based pretty much entirely on energy. So we can start to solve problems using this concept. Now, one other thing we probably should mention, and we already kind of did, is that we said energy can change from one form to another, but that means there must be different types of energy. Well, what types are there? Well, really, we can break these down into two main groups. Kinetic energy, which we abbreviate with a K, and potential energy, which we abbreviate with a U. Kinetic, we know for a fact, is some sort of motion energy. We know it involves movement. And it's pretty important that we're talking about macroscopic objects here. So if I move around, if I throw this stylus, if anything around you is moving that you can see, it possesses kinetic energy. Well, what about on the microscopic scale? Well, the thing is, though, is that if I zoom in, even though right now, if we said my body as a whole is not moving around the room, so it would say it doesn't have a whole lot of kinetic energy, but if we looked at all the molecules that make me up, they would be vibrating quite a bit. And those vibrations are all in random directions of someone disordered, and that would actually be more of thermal energy or heat energy. Now, there's a lot of connections between kinetic energy and thermal energy. That's actually a lot of the study of thermodynamics, which we explore in AP Physics 2. But for what we're doing in this course, we're going to pretty much treat them as separate things. Well, then let's also talk about potential energy. So potential energy is stored energy, and we can think of it as potential for motion energy. So the potential to have kinetic energy. And it's actually really position energy. And that's going to sound a little strange. And that's because it has to do with how objects in the system are arranged with respect to each other. Now, do not worry if that does not make full sense. We're going to talk about kinetic energy and potential energy a lot more later. They're going to have their own separate videos. So just stick with me right now. And there are a lot of different subcategories or flavors of potential energy. You can have gravitational potential energy, electric potential energy, magnetic potential energy, elastic, chemical, radiant, ionization, nuclear, all these different types. And you're familiar with some of these. For instance, chemical potential energy has to do with chemical bonds. Ionization potential energy or ionization energy has to do with the energy between electrons and nuclei, etc. But for this course, for physics, we're only going to be focusing on a couple of specific types. And that's going to be something that we call on the whole mechanical energy, which we often abbreviate with a capital E. So mechanical energy, though, only encompasses 1, kinetic energy, 2, gravitational potential energy, and 3, elastic potential energy. Now, typically, we don't put thermal energy in mechanical energy, but we are going to talk about that one occasionally as well. So now that we have some basics out of the way, we've talked about kind of a broad scope for this unit, let's start to focus on the specifics of this lesson, which is the concept of work. So work, which is abbreviated with a capital W, is a change in the mechanical energy of a system. So we can abbreviate this, or we can write kind of an equation for this, as W is equal to delta E, or delta is that change. Now, a few different things here. First off, if we look at this, you might be thinking, well, I don't know how to calculate energy, so how can I calculate a change in energy? Give it time. We will come to that in more details later, but we want to make sure we go ahead and understand now that a change in mechanical energy is known as work. Now, the units of both work and energy you probably are familiar with are joules, Joules, which we abbreviate with a capital J. And something else that's really important to go ahead and note now is that both energy and work are scalars. So energy has no direction. It's just a scalar quantity. And since work is a change in energy, it also has no direction and is therefore also a scalar quantity. Not vectors, just scalars. One other quick point I want to make sure I mention real fast is that when we talk about work, we often use this word very colloquially in English, like I'm working on something. And I want to be real careful here that in physics, a work is a noun. You do work, you perform work, work is done. It is not a verb. In physics, we do not work on something, we do work on something. Okay, well, how can these changes of energy take place? Well, first off, one way to do it is just to transfer energy in and out of a system, and the other way would be to transfer energy from one form to another. Both of these are examples of energy changes, and therefore both are examples of work. So to think about work a little bit more, let's really not worry about potential energy right now, and let's focus a little bit more on kinetic or motion energy. And how do we give objects motion energy? So let's look at the situation here. We've got this person about to do some maybe CrossFit or something and push this really big tire along the ground. And how would they give this tire motion energy? We can probably already think to yourself, well, how can they get it to move? Well, they would just apply a force, right? They would either push it or pull it. So applying a force will give an object motion energy. But how could we increase the amount of motion energy that is being given? Well, one, we can simply push harder or pull harder. If we increase the size of the force, we're going to be giving the object more motion energy because it's going to move faster. So that is one thing we can do, is we can increase the size of the force. Well, what else could we do? You might be thinking, well, maybe if we increase the time the force is applied. So not only if I push it with a bigger force, but maybe if I push it with the same force but for longer, that would also cause it to speed up, and speed up. It's going to have longer to accelerate. And this makes sense. It would be the increasing the time this force is applied, but remember, forces that are applied do not always result in motion. For instance, what happens if the friction between the ground and the tire was so big that when you push with this force, that it doesn't actually slide, it just stays there. So this would be like a static friction situation. Well, it doesn't matter if I push it for hours, if it's not moving, it hasn't gained any motion energy. And so with that being the case, we can say that time is not really the best way to talk about how much acceleration has taken place. So instead of time, we're actually going to look at something else. What's another thing we could use to quantify how long this force has been applied? Well, rather than increasing the time, let's increase the distance. So rather than applying a force for a length of time, let's apply a force for an actual length, for a distance. We must push this object through space for it to gain motion energy. If it's not moving, then it has not gained any motion energy. So not only applying a force, but it must be applied over a distance. And in fact, this gives us a direct connection between work and a concept we've already learned, which is force and, for that matter, motion. So we already defined work as a change in energy. But now we can say, well, if I increase the force applied, or the distance that force is applied for, I've increased the amount of change in energy, or the amount of work. So work is simply equal to force times distance, where force, the unit, is newtons, and distance, the unit, is meters. And so we can already see here that if we're getting joules from newtons times meters, well then a joule, 1 joule is equal to 1 newton times 1 meter. A newton meter is a joule. So let's look at a brief example to kind of figure this out. Let's say that the tire is pushed 2 meters to the right. What is the work from each force on the tire? So let's go ahead and draw an FBD for the tire, and let's say that the tire has some gravitational force of 500 newtons. The normal force from the ground is another 500 newtons. Let's say that it is pushed with a force of 1,000 newtons, and that the force of friction is back in the other direction, and we'll say it is 250 newtons. So if we want to calculate the work from each of these forces, well, we can just use that equation, work equals force times distance. So I'm going to go ahead and do that, and when I plug all these numbers in, I get, for instance, the work from the push would be 1,000 newtons times 2 meters, or 2,000 joules. From the normal force would be 500 times 2, or 1,000. Gravity would be 500 times 2 is 1,000, and the work from friction would be 250 times 2, which is 500 joules. But there are some issues here. Let's kind of go through these one at a time and see if this really makes any sense, because remember, work is a change in energy. So if we have a positive work, that means the energy of the object should be increasing. Okay, so let's look at the first situation. Let's look at the push. Well, if I look at the push, if I push it with 1,000 newtons over 2 meters, that's going to cause the tire to speed up. That's going to cause it to gain motion energy. So I would say, you know what? I think this makes perfect sense. This would be positive 2,000 joules. Perfect. But what about the friction? If we look at the friction, is the friction giving the tire motion energy? Well, no. It's actually causing the tire to slow down, or causing it to have to work harder to gain motion energy. So the work due to friction is actually a negative value, because it's actually causing a loss of motion energy. So the delta E would be minus, so the work is also negative. And what about the normal force and the gravitational force? Yes, gravity is pulling it down and the normal force is pushing it up, but the object's moving to the right. Do either of these contribute to it gaining motion energy? In fact, if it wasn't even moving to the right, we would still have those forces. And so the work from the normal force and the work from gravitational force, those are actually just zero. And they're zero because they cause no change in energy. Now, one last thing I want to mention here is let's talk about what is the net work on this system. And by net work, we just mean the total work, the summation. And so the net work would be, well, positive 2,000 plus negative 500. These are both zero. That would be a total of plus 1,500 joules. Let's look at a slightly different example and kind of reason through the same way we just did. Now, you're more than willing to try this one on your own, so feel free to pause it and give it a shot, but I'm going to go ahead and start going through it now. So let's say the tire is instead pulled 3 meters to the left. And if we see it's pulled by a rope, and it's pulled at this angle theta, where theta is 20 degrees. And what is the work from each of the forces on the tire? Well, once again, we have, in this case, gravity is still 500. The pull force is 800 newtons at 20 degrees. The normal force is reduced because the pole is at an angle, so that would be 225 newtons, and the force of friction is about 400 newtons. So let's go ahead and start with the ones we've already kind of dealt with. Now, we just saw that the normal force and gravity, they don't contribute to it moving to the left, so the work from both of those should just be zero. They are causing no change in the energy of the tire. And friction, additionally, would be causing there to be a loss in energy. So the force would be negative 400 newtons times 3 meters, or we get a total of negative 1200 joules. Well, let's talk about the pole force, though. Well, if we look at the pole force, what exactly are we going to have to do here? Well, if we look, there's actually two pieces to the pole force. There is the x component, or the horizontal component, and the y component, the vertical component. But which of these is actually contributing to the motion of the tire? We actually just want to focus on Fx, the horizontal component, because that's the direction the tire is moving. It's moving horizontally. The y components are really just helping to balance out gravity. So if that's the case, I'm going to say, well, then my Fd is now really just the x component times d. And well, what is f? This is theta. This is the adjacent side. So that would be f cosine theta times d, or 800 cosine of 20 degrees times 3 meters. Take our calculator, plug those numbers in, and we get 2255 joules, or positive 2255 joules. So what would the net work in this situation be? I just, once again, add all the numbers together, and we get a net work of positive 1055 joules. But as you saw, this equation doesn't really contain all the subtleties that it needs to for us to fully be able to understand how exactly forces contribute to work, or that change in energy. So we actually need to make an addendum to it. It's not just going to be force times distance. It's going to be specifically, I'm going to put two little lines here, and actually specifically what that is the symbol for parallel. So really, it's not just force times distance, it's the force parallel to motion in newtons times distance. We only care about forces that are parallel to the direction of motion, because those are the ones giving the object energy. So let's go through some different ways this could occur. Well, first off, if the force is in the same direction as motion, so if it's moving, we apply a force to it, it's going to speed up, so that's going to be a positive work because it is gaining energy. Well, what happens if the force is opposite direction of motion? So if it's moving some way and we push in the opposite direction, well, that would cause it to slow down or lose energy, so that is going to be a negative work. And lastly, what if work is just zero? One, if there's no force on the object, or really, I should say, no force or net force, depending on how we're looking at this. There's no motion, so there's no distance that the object is going through. Or the force is perpendicular to the motion, so the force and the motion are at right angles to each other. That's going to result in a work of zero or no change in energy. Now that is a more conceptual way to think about these problems, and that's a totally acceptable way to go about it. But let's say you have a particular situation and you're really not sure you're doing it right, and maybe you want to do a more mathematical way to ensure that you're getting the right value. Well, there's actually another way we can write this equation, which is Fd cosine theta, where F is the entire force in newtons, not the force parallel part. D is, once again, the distance in meters, and theta is the angle between the specific force we're talking about and the direction of motion of the object. So to see what we're talking about, let's revisit this example we just looked at a second ago, because we basically found the answers in a more conceptual way. But let's say we want to try it and make sure we get the same answer from a more mathematical standpoint. So let's go ahead and set everything up. So I'm going to put on all of these Fd cosine theta. And notice for all of these, I put the specific forces I'm talking about. And additionally, I put a little subscript next to the theta as well. Well, why is that? Well, because that theta is the specific angle between that force and the direction of motion. And what direction is this object moving? Well, it's moving to the left. And so let's go through these one at a time. Well, what angle is the force of pull directed at? Well, that's this force is 20 degrees away from the direction of motion, or 20 degrees away from the left. Let's go to the normal force. The normal force is directed upward. That is 90 degrees from the direction of motion. or in other words, from the left. The force of gravity is also 90 degrees from the direction of motion, or the left. And friction is, well, okay, it's really directed 180 degrees from the direction of motion. So I'm going to go and set these up. All I did was plug in numbers here. And if we remember our pre-calc class, and think about like the unit circle, for instance, well, cosine of 0 degrees is positive 1, cosine of 90 degrees is 0, and cosine of 180 degrees is minus 1. But that immediately tells us if I look at these three, I can plug some numbers in immediately. So specifically for the force from the normal force, cosine of 90 degrees is 0. That's 0 multiplied by this whole thing. I get a work of 0 from the normal force. From the gravitational force, it's also at 90 degrees, so it is also going to be 0 because cosine of 90 is 0. And for the friction force, cosine of 180 degrees is minus 1. So I'm going to multiply these two together, multiply by minus 1, so I get minus 1200 joules. And this one is cosine of 20, so I'm just going to do what I'd already been doing, and I get 2255 joules. So if you go back, you will see that these are the exact same answers. But we didn't have to think about as going with the motion against the motion perpendicular. This was a more mathematical way to go about it. Both methods, perfectly acceptable. One final thing I want to mention, up to this point we've only been dealing with constant forces, and if we look at that work equation, so W is equal to delta E is equal to F parallel D, well, there's no delta in front of that F. That has to be a constant force. What if the force is not constant? Well, when did we previously deal with a situation when we had a non-constant force? Well, that just came up in the last unit, talking about momentum, and we're talking about impulse. And when we dealt with this, we did a force versus time graph. Well, now, rather than a force versus time graph, let's actually utilize a force versus distance graph, or an F versus D graph. And if I have this graph here, how exactly could I figure out the work? Well, remember, work is F parallel times D. Well, how could I somehow multiply these two together? Well, let me actually make it the area under this graph. The area under the graph gives me the work performed on this object or system. Now, while we did spend a little bit of this lesson talking about some introduction to energy concepts, let's really go ahead and say, what are our main takeaways on the concept of work? Well, one, can we define work, and can we connect it to concepts we've already worked with in AP Physics? Well, one, we can define it as a change in energy, and additionally, we can connect it to the concepts of force and distance because it's equal to the force parallel times the distance. So can we therefore calculate the work done on an object by a particular force? Yes, we can do it that way, or we can do FD cosine theta. Can we determine if work is positive, negative, or 0 conceptually and mathematically? So conceptually, remember, if the force is in the same direction as motion, positive work. If it's in the opposite direction of motion, negative work. If it's perpendicular to motion, 0 work, or that's also if there's no force or no motion. And additionally, mathematically, we would use that cosine theta. We would do F as the entire force, D is the entire distance, cosine theta, theta being the angle between that particular force and the direction of motion. And lastly, can we determine the work done on an object from an F versus D graph? Yes, just by finding that area underneath the graph.